So at this point, we've looked at a lot of different ways that the derivatives of functions can affect the graph, right? Meaning the first derivative and the second derivative, and where we have a local min or a max, where it's increasing or decreasing, where it's concave up or concave down. So we can use all of these ideas now to get a pretty good picture of what exactly the graph of the function looks like without relying on a graphing utility. So let's just take, an example function. We'll try to make a pretty decent graph of it now. So let's use this one, for example, x cubed minus 6x squared. Okay. So if you were just approaching this purely from an algebraic standpoint without getting into the calculus, if you wanted to come up with the graph of the function, maybe first you would find the zeros. Okay. So x cubed minus 6x or 6x squared equals 0. So here you would pull an x squared out. You have x minus 6 equals 0. So x equals 0 and x equals 6 would be your zeros. So I'm going to make this graph here. Don't know exactly how big we're going to need it to be because we don't know where our inflection points are or critical points are yet, but we know our zeros now. We have one at 6 and one at 0. Okay. Maybe we would look for our y-intercept. Here the y-intercept is just at 0 itself. Maybe we look for the end behavior of the graph, which in this case we can see it does go this way and this way. Okay. And this was kind of the limit of what we could do with algebra, right? And we could do a sign chart too, maybe. So let's go ahead and write that out. So if we did a sign chart for f, then with our zeros and our other 0, 6, right? Then we can plug in some points here. So if we plug in 1, for example, this is going to be negative. If we plug in a negative 1, this will be positive. Or no, it won't. Sorry, this will also be negative. And if we plug in a like 7, for example, this will be positive. Okay. So this is kind of the limit, right, of what we could do with algebra. And we can make a pretty decent graph out of this. But now that we have these calculus tools, we can examine the first derivative and the second derivative, and we can come up with a better, clearer picture of this. Okay, so f prime of x is 3x squared minus 12x, right? So here we can set this equal to 0 to find our critical points. Let's see, we can pull a 3x out. So we get x minus 4 equals 0. So we have x equals 0 and x equals 4 as our critical points. And then we can do a sign chart for f prime. And it's kind of nice to lay these out, right beneath each other like this. Okay. So now we can look for the sign changes here. So if we plug in 1, for example, this will be positive. This one, the x minus 4 will be negative, so it'll be negative. And then it should alternate from there. So this will be positive. This will be positive. And I think that's about all we would need. So we can see right here, this is positive and then negative. So this is a local max. Okay. This one right here is a local min. Okay. So this is something we can kind of get the local max from the fact that it's negative on both sides of 0. So that kind of would have been reflected in our graph anyway, just with the algebra. But the local min would have been completely invisible, right? I mean, we would have known that there was a turning point at some point, but it would have been impossible to pinpoint exactly where that is without just like testing a lot of different values to kind of estimate it. So now let's go ahead and look at f double prime of x, so we can see the inflection point. So we'll get 6x minus 12 equals 0. So this is just going to be x equals 2, right? So we'll go ahead and overlay this again. And I'm kind of trying to line up the x values here, as you can see, right? So if we put in 0, this will be negative. And if we put in, say, 3, this will be positive, right? So there is an inflection point at 2, and it's concave down here, concave up here, right? And then also we know that the function's increasing here, decreasing here, increasing here. So all of this together, we can get a pretty good sketch of this graph now. Okay, so over on this side, we know before that first 0, we know that the function is increasing, and we know that it's concave down. Okay, so maybe we know it'll look something like this. After 0, it's still negative. It's now decreasing, and it's still going to be concave down until 2. Okay, so it's going to be concave down, but then here it's kind of changing, right? And then at 4 is where you also hit the local min. So maybe it's going something like that. It might be a good idea to actually find what these points are too, right? Like now that we know the inflection point is at 2 and that 4 has a local min, we know those are important points. So those might be points we actually want to put on the graph. Okay, so f of 4 is 64 minus 6 times 16, which is 96. So this is what, negative 32, I think. Okay, so it's going to be really far down. We'll just say that the scale is, let's just say that's negative 32, just so we don't have to draw a huge graph here. We never actually defined the y scale, of course. F of 2 is going to be 8 minus 6 times 4, 24, so negative 16. So we'll say that's about halfway there, so about where we drew it. Okay. And then after 4, it's going to be increasing, and then it's going to be, it's going to go through the 0 at 6, and it's going to be concave up this the whole time after 2 as well, right? So something like this. Okay. If you're doing this on a test or something, of course, it's kind of hard to draw, so you could just kind of label your inflection point, right? Like maybe you put inflection point just to make it clear exactly where it is. Min, local min, right? So let's go ahead and jump over to Desmos and compare our graph to the actual graph. Okay, so we have x cubed minus 6x squared. Okay. And of course, our scale was a little bit different, but ultimately it looks pretty similar. It's way more compact, right? Because they're actually using the full scale here. But you can see kind of how it's concave down until 2, and then concave up after that. We got the local min here at 4, negative 32. Local max here at 0, 0. 0 at 6. Okay, so we have a pretty good, clear picture of this graph now. And, we can do this with pretty much any graph, right? 6x, or x cubed minus 6x squared. Really not special here. We can do this with anything. So in general, you find the first derivative, find your critical points. Find your second derivative, find your inflection points, do sign charts for all of them overlaid on top of each other, and then you just have a blueprint right there of exactly how to sketch the curve of this graph.